Okay, so let's begin. I'll recall what we started yesterday. So we started proving the basic version of the moving lemma. Okay, so yesterday when I stated this, I assumed that the base field is algebraically closed of characteristic 0, but yeah. So now it seems that just assuming that the field is infinite is enough. Okay, so let X be a smooth projective variety.
What you wanted was a projective subspace
to project from and
infinite plus one.
Yes. And let alpha and beta be cycles of dimension R and S. So then there exists a cycle alpha prime which is rationally equivalent to alpha such that alpha prime and beta intersect properly.
If this happens over a finite extension of your base field, can you do a proper push forward and get it back to the extension formula, etc.?
So there is a projection formula. So which for flat proper morphism, so which says that if two cycles below are, if one cycle above and pullback of another cycle from below intersect properly, and then you can push it down. And then the push forward of the first one will intersect properly with the original.
So this removes all that. Because you always have your.
So you can always choose an infinite extent.
It will be defined over a finite sub extension, therefore proper.
Yes. Yes, but okay. Presumably that's correct. Yes. So, but let's see the proof and then be sure. So most likely infinite can also be dropped, as Nitin just pointed out, using the projection formula. So yesterday I indicated an idea of proof. Today I will give slightly more details, but to do the proof in full generality with all dotting all i's and crossing all t's is going to take a long time. So I will cut some corners. But so the proof of as far as the proof of this statement is concerned, there are no doubts in the literature. So this proof is correct. So let's see this. So of course the proof. So by linearity we may assume that alpha is represented by a subvariety, a closed subvariety. So for some r dimensional closed subvariety, beta equal to some linear combination of ni's and ti's, where ti's are subvarieties of dimension S. So my X will always have dimension D. So D will be reserved for dimension of X. Okay. So we want to prove the statement by induction on the maximum of the dimension of the intersection of Z with these closed subvarieties Ti appearing in the expression of beta. Okay, so this number, as we know, is always greater than or equal to R plus S minus D. Okay, so the base case is trivial, right? So the base case means that all these intersections they have dimension exactly R plus S minus D, in which case the intersection is already proper, so there's nothing to be done. So let's assume, so the case, so nothing to prove in the case E equal to R plus S minus D. Okay, so assume E is greater than R plus S minus D. And now, so I wrote two ingredients. So the first one, let me make a little more precise today. So let me call it lemma 1. Okay, so choose an embedding of X into some projective space. So the idea was that inside Pn there are lots of rational equivalences and it's easier to move. Okay, so we take the picture to Pn and there we we find a new subvariety intersecting X properly, which will have a particular description. Okay, so so the lemma says that there exists a subvariety C of Pn intersecting X properly such that, okay, so if you take the intersection product of C and X, so in this, so Z will appear with multiplicity 1, so inside C intersection X, and then the rest of the components will be such that they will satisfy the induction hypothesis. Okay, so what does that precisely mean? So where, so this such that this happens with each Zj subvariety of X of dimension R, Z not equal to Zj for all j, and dimension of, so now we have to ensure that this cycle intersects beta properly. So we have to look at intersections of Zj's and Ti's which appear over here. So then the condition is that dimension of Zj intersection Ti, this is less than or equal to dimension of Z intersection Ti with strict inequality if Z does not intersect Ti properly. Okay, so this is the statement. So then this would basically mean that the induction hypothesis can be applied to this part. So this equality is in Pn, but the claim of the lemma is that Zj's are actually going to be subvarieties on X. So
Z, what is the claim?
Z is already a subvariety on X. Yeah. So everything is happening on X, but this C dot X is, I mean, the C was not inside X, C is outside. I mean, it can be outside.
So that equality is in Chow group or in Z cycles?
Everything is in cycles, no Chow group yet. Everything, all the equalities are in, so this is, I mean, so to speak, is in the image of cycles on X inside the cycles on X cross Pn. Oh, no, sorry, what am I saying?
C dot X was only defined.
Sorry, so cycles on X to cycles on Pn. There's an embedding, closed
C dot X belongs to it. Or is rational equivalent to no rational.
No rational equivalence. So C and X, both are subvarieties in Pn. Okay, so the intersection takes place inside cycles on Pn.
Or inside the Chow group.
No, cycles on P, cycles. So there is no rational, I mean, we don't yet know that it passes through rational equivalence. So, yeah. So this is happening inside Pn, but these, So the claim of the lemma is that the
So maybe the clarification is that since C and X intersect properly, C dot X is well defined without any rational.
yes, C dot X is well defined without any rational equivalence. Yes. So we only know product at the level of cycles by now, which intersect properly.
Okay. This line, thank you, bro. This line C intersecting X properly takes care of my question. I am not clear.
This. Okay. So yeah. So I will not give a detailed construction of how C is obtained, but I will give you the procedure in which it is.
So to speak, these MJs, these coefficients are computed on projective space.
The coefficients are computed on the projective space. The coefficients are.
Some cycle.
The coefficients are, that's a good point. Coefficients are computed on the projective space, but then they give you some integers and then the cycle comes from the image of some cycle on X inside Pn. Okay, so how to choose this C? So this C is obtained by taking the closure of some subscheme which is pulled back from an image of successive projections. So you need some. So anyway, let me write it down a little more precisely. So choose. Close points little x in Z and xi, so I've used j I think here, so xil in every irreducible component. So TIL of TI intersection Z. So okay, so what I mean is that TI intersection Z will have some irreducible components. Pick one close point from each of them and pick one in Z. Okay, so now what are we supposed to do? So the claim, which I am not going to.
Distinct?
What?
Distinct?
Yes, all distinct. Okay, so the claim is that there is a sequence of projections.
I mean, I'm just thinking, how can I ensure that little x is different? Because if it's a positive dimensional variety, the ground field is different.
You don't need the infinite ground field. He's not saying rational. So I don't think the points have to be
Closed, only closed, or you mean not even
you want to basically avoid these points.
I want the projection to be étal at these points, and when you restrict to Z locally an isomorphism and so on.
Okay, fine.
Okay, let's see. But anyway, the point is.
But keep in mind that if they're not, I mean, it may affect the things later on.
Let's see. So I think, but anyway, if our field is infinite, we can do this.
You can have what Srinivas is pointing out, if the intersection is zero dimensional, then it may be a problem.
If the intersection is zero dimensional and there's only so then.
Many points, maybe.
But then you'll have to take just those.
Doesn't work. You have to think a little bit.
Yeah.
This has nothing to do with infinite field. You're simply taking closed.
So the infinite, I'm just taking close points. I think the infinite field is required when I take projections, because then I don't want the thing to run out. I mean, if the field has too few points and then the difference between the dimension is too huge, then there might be a problem. So, yeah.
Suppose TI intersection Z and TJ intersection Z are same and is a single point, then we cannot ensure distinctness. Like say T1 intersection Z is a point, T2 intersection Z is the same point.
So the thing is that if the components are distinct, then only you can ensure.
Distinct components may intersect Z in the same.
Distinct components may intersect Z in the same point. In which case you just. In which case, but then the TILs will. Then okay. So the thing is that T1L and T2L. If there's only one, then which one do you pick? So you have to take, so you have to avoid repetitions like this in here. So anyway, is the point clear? No, you just pick, so say it might happen that T1L and T2L may be same. Okay, so in this case I don't want to count them twice, I want to count them only once and pick a close point.
No, it's not T1 and T2 and T.
Then?
They may be different, but they may go meteors, right? In the concept.
Yeah, but these are components of Ti intersection Z.
Oh, they are not the original case.
No. They are TILs are components of Ti intersection Z. So I just don't want repetitions there. That's all I'm saying. No. Two different components may intersect Z in the same thing. That's the point, right?
TIL may be the same as TJL.
Yeah, TIL may be the same as TJL, but you don't take repeat. Yeah, which may be a singleton in top of that, in which case you have no choice but to take that point. Okay, so yeah.
Anyway, we'll see how it goes.
Yeah. Anyway, I'm not going to prove the claim, but I will write the claim. Okay, so there is a sequence of projections. Yeah. So by projection, I mean projection from a point. You have a point in a projective space, then you can project from that point to a hyperplane, so which will be a projective space of one dimension less, right? So our projective space started to start with was this P to the power capital N, P capital N, okay, of dimension capital N. So the points will be of this type. So P N minus some point, let me call it P N to P N minus 1.
And so that point has to be k rational, that P0.
Yes.
So
All
your field has to be infinite at this stage.
at this stage, yes. All these points I want to be k rational because everything I want projective spaces over the base field. Okay, so yeah, so P N minus 1 P up to P. So up to you reach PD, where D is the dimension of X. Okay, so and I have to write down the conditions, how to choose these things. PD, such that. So the claim is that these points can be chosen suitably. Okay.
Doesn't that amount to a single projection from a lighter dimensional projection?
Yes, it does, but it's easier to of course, but it's easier to see. I mean, handle each projection one at a time. Let me write down the conditions that I want from the.
Sir, I have another question. Suppose R equal to 0, then also you cannot guarantee a distinctness, right? Like suppose that Z is a single point, but it may be inside some Ti. So we have to move the point outside each of the Ti's. So how can that be done?
His question is R is equal to 0. I am trying to see that if R is equal to 0, what would this be?
Just if Z is inside Ti, then it is the point, but we need to ensure that it is not in any of the Ti's.
No, my feeling is that then you will already be in the base case. No.
No, the point lies inside here doesn't mean it properly. When you do your interaction, ZJ is better. So ZJ is gone outside.
I see.
Z is a point in this case, right?
I see.
Z is a point.
Yeah.
Then ZJs will also be points and then Z will point. That's what you have.
Just a point.
Yeah, so then ZJs will also be points, and then now I have.
It will be outside, and that will be your moment. That's what you want.
Yeah. So actually, so the thing is that the way the projections are chosen, so then that point will be forced to be this X, right? And then the proof will work. Let me just give the conditions, okay? So let me give some names. So let me call this R n minus 1 R d plus 1. And let me call pi to be the composite of all of these. So okay, so in the right order. So this is I guess I have to start with the last one first. Okay, so so there exists a sequence of projections such that so A. So this pi, this map pi restricted to Z from, restricted to x from x to PD is finite. Then pi is étal at x and the x il. Now if you restrict pi to z, which is a subvariety of x, so then this will go from z to pi of z inside PD, and this will be an isomorphism in an open neighborhood of all these xils. Okay, so I mean each xil will have a Zariski open neighborhood over which it's an isomorphism. And then the last, then two more. So if you take this Ti, which is in the expression of beta, and you intersect it with pi inverse of pi of z. Okay, so pi of z is the projection of z. You are taking its inverse image. So there might be extra things which project to this pi of z. Okay, so this will definitely be contained inside. Okay, so this will be contained inside. Okay, no. Anyway, so what I want to say is that this will definitely have Ti intersection z, but there may be something extra. Okay, so what is this? So what are the good properties that you can expect from what is extra? Okay, so that's the thing. So you have to expect some sort of a dimension bound on this EI. And what is the right dimension bound? So this EI is supposed to be closed inside Ti, and its dimension is at most r plus s minus t. Okay, so where EI of dimension at least at most r plus s minus. Okay, now if you choose this, choose the projections this way, so this can be done by some sort of general position arguments, but anyway, I'll have to, so to do this in detail it takes some work, but let's assume this for the moment and let's see how C is going to be obtained. So what you do for C is that, so you take, so for C you take this pi of Z, pull it back and take the scheme theoretic closure inside Pn. Okay, so so the next condition would be that C, which is defined to be the closure of, so this pi inverse of pi Z closure inside Pn intersects X properly. Okay, so this, now one has to do this by looking at what projection does to subvarieties which are of, to subvarieties which are properly contained inside Pn. Okay, so I will take this for granted. Okay, for now. Okay, so the point where you use that this is étal at X is to ensure that Z occurs as multiplicity 1 inside C dot X. Okay, so this also requires a calculation to check this, but this is where this thing is important. And so we proved a lemma last time that if a component occurs with geometric multiplicity 1, then its intersection multiplicity is also 1.
You mean pi restricted to X is étal?
Yes, I should have written. Yes, I should have written that. X is non-singular, and So to make it finite, of course, you have to cut down until until the dimension of x, projective space of the dimension of x. Okay, so yeah. Okay, so if this is done, so then your C dot x will have the desired form. Okay, now okay, so yeah, one more thing that I should say is, so how do you guarantee that these ZJs are subvarieties of X of dimension R? Okay, so there is some argument required there, right? So this, so for yeah, so for this, okay, just a minute. Let me see. Where did I?
Why restricted X is finite? Why is a finite? Restricted X are finite possible.
Yes.
So the inverse image of something of dimension R will be dimension R.
Will remain dimension R, so that's not a problem. But yeah. Okay, so that's okay. So pi restricted, yeah, as Srinivas pointed out, this is finite, so that will not be a problem. So that this ZJs will be of right dimension.
Less than or equal to R in any case.
Yeah.
But greater than or equal to R is forced by your other.
Yes. So okay. So if we yeah. So no. Anyway, I was just no. What we want is this condition to be satisfied. Okay. So dimension of ZJ intersection Ti should be less than or equal to dimension of Z intersection Ti with strict inequality if Z does not intersect Ti properly. Now. Yeah, so basically you have to look at each irreducible component of ZJ intersection Ti and then argue about it using B and C that this will happen. Okay, so the thing that it is an isomorphism, so this projection on Z is an isomorphism in these neighborhoods of XILs, and these XILs are in the irreducible components of TILs is supposed to guarantee that this condition is true. So okay, so this also requires a small argument which I will not write down in detail, but the argument goes as follows. So you take a component of this, then you have to argue two cases. It will either be here or here. If it is here, then there is no problem, that equality will be satisfied anyway. But if it goes to EI, it has that condition by the choice of the projection. So that's one small argument that is required. Okay, so yeah, so just for the reasons of time, I am actually not writing this all out in detail, but yeah, this works. So now once you get this, so you can the induction hypothesis applies to each ZJs. Okay, so that means that you can find a cycle rationally equivalent to this part which intersects beta properly. Okay, so so now let's go to the next ingredient. Okay, so this says that there exists a closed subvariety C prime, yeah.
But you needed something more about the close points. You need them to be smooth points of it. Otherwise, how will it give it up? The image down there.
No, the locus of such points for which this happens will anyway form an open set.
No. So it's not eternal thing. You need not. The point can be. The image will also be equally bad.
Yeah. So the second lemma was that there exists a closed subvariety such that, so if you take the projection from C to P1, this is dominant. then if you take the fiber over 0, this is just C, then C, okay, I think he asked me to write a little more. So C and X cross P1, C prime and X cross P1 intersect properly. And the fiber over infinity intersects each Ti properly. Okay, so I'll just give again idea of proof. Okay, so how would you so how to choose such a thing? So write, so this actually comes from linear algebra. So you write Pn as, say, P of projectivization of a vector space V. So this is vector space of dimension n plus 1, and so let E be endomorphisms of V. So now inside this, and look at the projectivization of E dual. So now inside this there is a point corresponding to identity of V, and what you have to do is take a general line through this point. Okay, let me just write. So take a general line L inside L passing through, so L inside P E dual passing through the point corresponding to the identity of V, and take C prime to be the image of L cross C inside this projectivization of E dual cross projectivization of V. Okay, so that's how now so the main point of the proof is to choose this line suitably so that these two happen. Now, so the way to do this is to just see the bad set of this, and then this will be a small closed set, so you can avoid it. That kind of an argument. Okay, so anyway, I'll again not write details in this case, but this is how C prime is chosen. Okay. Okay, so now to complete the proof. Okay, so this was, I guess, almost clear last time, but anyway, I will just rewrite it for the, again, just for the sake of completeness. So now, so lemma 1 gave us this C.
In your statement B, it's
Yeah.
not just any isomer, it's that particular isomer.
It is, yes, it is,
So it looks like an abstract isomer.
no, so maybe I should write E.
Equal.
Yes, it's physically that C. Okay, so so now lemma 1 gave us that C, and now using that C, using lemma 2 we cooked up C prime. So now so now define gamma to be, so now we know that C prime and X cross P1 intersect properly, so you take their intersection product, which is defined as a cycle on Pn cross P1. Okay, now we claim that, okay, so let me just first make an observation, although this is, I think in some sense this has come in probably Nitin's lecture, but yeah, so if W is a subvariety of X cross P1 and it intersects X cross A properly for a k rational point of P1 A, then so if you look at the fiber of W over A, so you take the map W to P1, you take its fiber over A, what can you say about the cycle associated to W of A? So this is just the intersection of W with X cross A. Okay, okay, so this. Okay, so where is this intersection product considered? So it's considered inside X cross P1. Okay, so but yeah, so on X you can also write W of A equal to, if you take the projection to X and then push it forward, then you get this equality on as cycles on X. Okay, so W is a subvariety of X cross P1. WA is the, as I used in the previous proof, so W has a map to P1, right? So the fiber over the rational point A. Okay, so I guess probably I gave this as an exercise yesterday, right? In one of the properties. So yeah.
The intersection actually is well defined as a cycle in either of the two.
Yes, that's no. This is, so this a priori is inside X cross P1. Now I'm pushing that down.
Yeah, but as a cycle, it is well defined.
The left hand side is yeah, curiously well defined.
The intersection of two cycles is well defined as a cycle.
As a cycle on X, yes. On either of the two, or on X or on X cross.
Therefore, it's well defined as a cycle in X cross A, which is what we have.
Yes. Okay, so now what do we want? So our claim is that this C dot X, this is the projection, the push forward by projection applied to this gamma dot X cross 0. Okay, so we are going to use that. So this gamma is the intersection of C prime and X cross P1, and the fiber of C prime over 0 is equal to C. That's what will give us this. So this is easy to see, right? So this we will do using the associativity of intersections, which I talked about yesterday. But there, while using it, you have to be careful about all the three things pairwise intersecting properly. I mean, in the rest of the time, I'm going to say something about the other moving lemma. There, this kind of problems actually cause a problem. So, yeah, anyway, so how do you check this? So you just calculate this. So this will be the projection on C prime dot X cross P1 and then dot with X cross 0. So check that all these intersect properly. So you can use associativity to say that this is C prime dot. So this is C prime dot the intersection of X cross P1 and X cross 0. So which is again So this is it is X cross 0, but I was just trying to see if okay, X cross 0. Now what I want to do is So what I want to do is I want to also use the commutativity to intersect X cross 0 with C prime first to get C. Okay, so I'll use commutativity and associativity both to put this over here. So I've brought X cross 0 in. So then this is C prime 0 dot X cross P1, but this part inside is just the projection upper star on X, right? So So now I will use the projection formula to say that this is okay. So that's the thing. Okay, so I took x cross 0 first inside here to get C, and then use the projection formula to conclude that it is C dot x.
Let's make a small remark.
Haha.
In A equals dominant is flat.
Yes, yes. So yeah, so this is dominant, so it is flat. See, you can use projection formula only for flat and proper morphisms. Okay, so now how to finish the proof? So this is this. So let me call. So let me call gamma 0. Let me denote gamma 0 by this, just so that it's yeah, easier to see. Or let me write gamma A to be equal to this for x cross A. So then you know that gamma 0 is rationally equivalent to gamma infinity. And what is gamma infinity by this condition of the lemma? It just says that it intersects your beta properly. Okay, so yeah, so gamma infinity intersects beta properly because it is supported on C prime infinity. Right, so so this D condition gives this, and now the proof is over. Right, so just to yeah, so then so you have this equality equal to yeah, so gamma 0. So you know that Z is gamma 0 minus MJZJ. So this is rationally equivalent to gamma infinity minus a cycle. So now you replace this by a cycle which is so delta, which is rationally equivalent to this MJZJ and intersects beta properly. Okay, so then we are done. So we have got the desired cycle. Okay, so okay, is this okay? So I understand this proof is a little complicated because I have not explained the geometric input, how to arrange the general position arguments. Okay, but the provided you can do those things, I mean this yeah, should be fine. Okay, so now in the rest of the time I am going to yeah, go into some dangerous territory, trying to prove that if alpha is rationally equivalent to 0, then the intersection product, and alpha and beta intersect properly, then the intersection product is rationally equivalent to 0. Okay, so the thing is that the original proof of Joel Roberts has a gap, and De Jong in Stack's project has claimed that the gap can be I mean that part can be corrected. I see the proof that and it seems fine to me, but yeah, I ask you to yeah, look at it carefully and challenge me. Huh?
Be especially careful.
Yeah, be especially careful, but it looks okay. So let's see the yeah. Okay, so here's the theorems. Okay, so so let X be smooth projective over K. And let alpha in R cycle and beta and S cycle intersect properly. So if alpha is rationally equivalent to 0, then the intersection product is rationally equivalent to 0, is what we claim. Okay, so so let's do a special case first. Okay, so let me put it here. So let W be a subvariety of X cross P1, be a subvariety of dimension S plus 1. And so dominating P1. Okay, so let V be an R dimensional subvariety intersecting okay, so let me say W0 and W infinity properly. Okay, so then if you take the intersection of V and WA, this is rationally equivalent to, sorry, I wrote the original thing, so with 0 and infinity. Okay, so is the statement clear? So this is what we'll go into, this is a special case of the theorem. See, the theorem is going to reduce to just taking beta to be a single subvariety, and then anyway, so okay. Yeah, okay, anyway, but then just be very careful in this proof. So anyway, so what do we have? So let me indicate a proof. So what do we know? For any A, we know that this WA, which is the fiber of W on P1, this is obtained by push forward of the product of the intersection product of W and X cross A under the projection, the push forward by projection to X. Okay, so now what does the projection formula give us? Yeah, so we are interested in V, the intersection product of V and W0. So we'll take A equal to 0 and infinity soon. So we are interested in the intersection of V and WA. So which is supposed to be, so yeah, so now so you are intersecting with V here, and I want to use the projection formula. Okay, so take this projection of the push forward by projection of X outside. Okay, so what should I do? So I take this projection out, and so there was V dot this thing. So I have to replace this by the pullback of V, which is going to be V cross P1. Okay, so now be very careful here. Okay. So now for A equal to 0 and infinity, we have to check that these are rationally equivalent. If you could, so now it's very tempting to use the associativity of intersections and then get the result. But that is a problem. This is the mistake in Joel Roberts' thing, because V cross P1 and W may not intersect properly. Okay, so you can use associativity of intersections only if these intersect properly. Okay, but they don't. And so the claim is to replace this. We don't know that they do. I mean, yeah, it's not clear at all that they do. Okay, so these may not, may not intersect properly. I don't know if this is visible, but okay. So now, what to do? So I mean, you would in general have. So if this worked, you would have the intersection product of V cross P1 and W. So you have to replace this with another cycle, but maintaining the properties that you want, something like that. Okay, so that's what, and then you have to cook up a rational equivalence using some other cycle. That's the idea. Okay, so you look at the intersection of V cross P1 and W and look at the irreducible components. So let Zi be irreducible components of V cross P1 intersection W. Now what can you say about dimension of Zi? So this is at least greater than or equal to, so the dimension of V cross P1 is R plus 1, the dimension of W is S plus 1, and minus the dimension of X cross P1, which is D plus 1. Okay, so this is R plus S plus 1 minus D. Okay, now V and WA intersect properly for A equal to 0 and infinity. This just means that the dimension of so now I look at the fiber of this Zi over A. So what's the dimension? So this, so Zia, I mean there's no reason for Zia to be non-empty. It can be empty. But if it is non-empty, then what is the dimension? The dimension is going to be exactly one less than this. So this is going to be R plus S minus D. So I'll just write if non-empty. Huh? No, Zi so is inside X cross P1, right? So A is the fiber over P1, or fiber over A in P1.
So Zi is the fiber of Zi over.
No, Zi is an irreducible component of V cross P1 intersection W. This is taking place inside X cross P1. There is a map to P1. There is a map to P1, and A is a rational point in P1. So the fiber, so the inverse image of this. Okay, so that is Zia. So what can you say if Zi intersects X cross A? Okay, so then Zi has the right dimension, right? So if Zi so meets X cross A, then dimension of Zi is R plus S plus 1 minus D, and also the map from Zi to P1 will be surjective. Okay, so yeah, so then and yeah, so Zi inside X cross P1, this composite is surjective. So now divide this I into two parts, one where this is surjective and one where it's not. Okay, so write I equal to I prime disjoint union I double prime. So where I prime is precisely the set of I in I such that yeah. Okay, so now the idea is to cook up a cycle only using these Zis. Okay, and throw away the I double prime. Okay, so consider gamma equal to I in I prime EI Zi. So where now for EI, if you want to do the right thing, yeah, there is no choice. It has to be given by the Serre-Tor formula. Okay, so what should it be? So the alternate sum of lengths. So lengths where? So you are calculating inside X cross P1 localized at the generic point of Zi. Okay, so inside this by the correct Tor. Okay, so we are looking at the intersection of V cross P1 and W. So this will be localizations of those at the generic point of Zi. Yeah, okay, I forgot to say one more thing. So, okay, so this thing is surjective for those I in I prime. What about the I in I double prime? What happens? So it has to be a proper subvariety, right? Proper meaning of lesser dimension, and Zi is irreducible. So it has to be a point, right? So if this Zi is not dominating on P1, the image has to be a point. Which has to be different from 0 and infinity, because at 0 and infinity the intersection is proper. Okay, so they are inside I prime. Okay, so suppose that the image of Zi to P1, this is equal to Ti, some point for I in I double prime. Now I want to look at the open set, and I want to throw out these points. Okay, so let U be P1 minus these things thrown out. Okay, so now what do we do? So we focus our attention, instead of x cross P1, to x cross U. Okay, so look at so now consider x cross U and look at so what are the three subvarieties in question? V cross U, not V cross P1. Then W, it's fiber over U, the inverse image over U, and x cross A, for A equal to 0 and infinity. Okay, so consider this x cross U, and so the subvarieties so V cross U, so the inverse image of U the fiber over U in W, and x cross A for A 0 and infinity. So these intersect properly pairwise. So that's not the only condition for associativity of intersections. You also have to have the expected dimension of intersection of all three of them, but that is there in this case, because now you have thrown out the bad points inside x cross U. Yeah, so now what happens if you intersect V cross? So here we had to worry about this intersection, right? So now restrict only to x cross U. Don't look at x cross P1. Okay, so the intersection. So the reason is that the intersection is going to be supported on x cross U. So what I want to say is, so V cross U intersection of WU dot x cross A. Okay, so what is this? A is 0 or infinity. Yeah. So in general A is in U. So what is this? So now I will use associativity. Okay, so as cycles on x cross U. Okay, so now what is the restriction of the cycle gamma to x cross U? Okay, so this is a question. So this a priori is a cycle on x cross P1. Okay, so what is its restriction to x cross U? So it is this. Okay, because we have thrown away the bad components coming from I double prime. And okay, so this thing is the restriction of gamma to x cross u. Okay, so now, so on the other hand, we have to still look at, this one. So let me keep this. Okay, so what about the restriction of this v cross p1 dot w dot x cross a? So what is the restriction of this to x cross u? So this is the this side. Okay, so these two cycles on restricting to x cross u agree. Okay, and that is enough to cook a rational equivalence, is the argument. Okay, so so restricts to so this v cross u dot okay, so then our claim is that, so if you, so this is the cycle that we originally have, right? We come from, I mean, we have to worry about this cycle. What? No, u. Yeah. Okay. No, what I want to say is, yeah. So I want to claim that, so this is the cycle that we want. So this is equal to gamma dot x cross a. This is what I want to claim. And yeah, so the so everything is happening, a priori everything is happening inside x cross u, and restricted to u, x cross u, these cycles agree. So on the smaller thing they have to agree. Okay, so so this is supposed to be the workaround for this. I mean this this problem of not being able to use the associativity here itself and cause a thing. Okay, so now we just have to finish the proof from this, which well, the point is that now you know that for a equal to 0 and infinity, these guys are rationally equivalent to each other. So the ones required in the theorem are rationally equivalent to each other. Okay, is this fine?
So you could put it differently by saying that the things which break associativity don't lie in x plus a.
Yeah. So things which break associativity are outside the support of the cycle that you are interested in. So you just throw them away and yeah. So that's the idea. I hope it is correct. So let's just maybe now everybody can. I mean, I could not find a fault in this. So now it's up to everybody to go home and check. Yeah. So okay.
You have to compute for each component of the intersection. You have to see that the components of the intersection and those components it agrees properly.
Yes.
And that the multiplicity that you are calculating are the right ones.
Yes.
Now,
yes.
And those components it agrees properly because it doesn't intersect x plus a.
Yes.
The bad components don't meet x plus a. And now the multiplicity computation is in fact associated.
Yeah. Because this can be.
Because the TOR formula is fine locally at that.
Yeah, it's fine locally, and you can do the whole computation on x cross u and not on x cross p1.
It's only the local rate that you are doing the TOR.
Yeah. The TOR computations are local, so that's that's fine. Okay, so so this so since I'll just gamma x rationally equivalent to gamma intersection with x cross infinity. This implies the lemma. Okay, so now the main thing is not over yet because we have to prove the theorem. So this so again we'll have to use the lemma 1 and lemma 2 that I had mentioned while proving the first part of the moving lemma, the easy part of the moving lemma, the so-called easy. So, well, they will have to be used again to the proof, but anyway, we will do that now. Okay, so. So recall that the theorem said that if alpha is rationally equivalent to 0, alpha and beta intersect properly, then the intersection product is rationally equivalent to 0. So by linearity, you can assume that beta is given by just single subvariety. Okay, so alpha is rationally equivalent to 0. So this is given. So we may assume beta is given by some subvariety, okay, let me call it Z. So for some of dimension S. Okay, and so it is given that alpha intersects Z properly. Okay, so yeah. So what does it mean to say that alpha is rationally equivalent to 0? So you know from the last week's thing that so there exist finitely many R plus 1 dimensional subvarieties. So Wi of x cross p1 such that alpha is the sum of Wi0 minus Wi infinity. Okay, so that's the definition of rational equivalence. So we will have to look at okay, we are intersecting, so we'll have to look at irreducible components of Wi0 and Wi infinity and yeah, make an argument. I mean, see what the condition that they intersect properly gives us and then calculate. So okay, so let me just try to write it like this. So for a equal to 0 and infinity and t in some indexing set j be all the irreducible components of Wi's. Okay, so I don't want to write some new dummy variable from 1 to something and so on and so forth. So I'm just taking all the irreducible components like this. Yeah, so the proof of this is also going to be on the induction of the dimension of intersection of Z with these irreducible components. Okay, so it's a proof parallel to the first proof that we saw at the beginning of the lecture. Okay, so we'll do induction on n, which is the maximum of the dimensions of Z intersection I don't know how I'm writing. Yeah, okay, I, A. Okay. Yeah. So here there is one thing that one has to keep in mind. So it's given that Z intersects alpha properly, but this does not imply that Z intersects these guys properly, and so one has to be careful. Okay, so this intermediate subvariety is giving the rational equivalence. Their intersection with Z need not be proper. Okay, so that's the problem. Okay, but so in that case, what will happen? The dimension of these intersections will be greater than strictly greater than this R plus S minus D, the expected the good dimension number. Okay, so what is again the start of induction? So this is, this is always greater than or equal to R plus S minus D, right? So the start of induction is clear. Why? So then it means that it intersects all these WIATs properly. Okay, so then there is no problem, and then you can just conclude. There is nothing to do. There is not nothing to do. It's done by the lemma, the previous lemma. Okay, so the case n equal to. Okay, so now we have to do the induction steps. So suppose that this n is strictly greater. Okay, so now we will use those lemma 1 and lemma 2 again to get nice, we put everything inside Pn, get subvarieties with nice form. So this lemma 1 implies that there exists C in Pn intersecting X properly with this C dot X given by Z plus summation Mj Zj. Okay, and such that, so what's the condition on Zj? So the dimension of Zj intersection with each of these WIAT, yes, so that's going to be less than or equal to the dimension of the intersection of Z with those things with strict inequality if Z does not intersect properly. Okay, so those kind of things. So basically, so for this the induction step is the induction hypothesis is applicable as usual. Okay, and now so by lemma 2 get C prime so this C prime 0 equal to C, C prime and X cross P1 intersect properly, and so C prime over infinity intersects all these WIATs properly. Okay, so so where A is 0 or infinity. Okay, so now can we finish the proof just along the lines of the previous proof?
So we are actually going to write the WI may not intersect properly.
So Z may not intersect these properly. Right, so if Z intersects, that's the base case for the induction. Okay, so if so it may not intersect, so then by this this lemma I want to single out Z and the rest of the part which intersects properly by going to a projective space, and then again there will be a rational equivalence between C0 prime and C infinity prime giving the thing. Okay, so
WIs are changing with each induction step.
No, so these WIs are, see, at some point you will have to replace this with a rational equivalence to something that intersects properly, right? So the WIs that coming there are completely different. Okay, let's start again. So when we start with the base case, then we know that Z intersects all the WI 0 T's and WI infinity T's properly, and then by the lemma we know the result. Okay, so now we are assuming that n is greater than this. Okay, so now so I get a subvariety of, so then I get this C like this, and then I get a subvariety C prime such that the infinity, the fiber over infinity intersects all these WIs properly. Wi zeros as well as Wi infinities. T's. Meaning the components of of Wi0 and Wi infinity.
Yeah, so I was second statement is kind of replacing Z by something which is better here. In order to get, so beta is equivalent to something which is better here.
Yes.
Then those components again lead to the index.
Yes. Beta is that's true.
Question was whether we are
No. I thought because we have taken beta to be a subvariety. I thought you are replacing it with another subvariety and no. The cycle, yeah.
actually beta is being replaced by
Yes. So okay. So should I write down the rest of the proof for the completeness, or people seem to be already very confused? So I think I'll just complete the proof. So because this is quite confusing.
Intersection theory has been constructed in the style of Coulter, right?
So that is what.
Therefore, this conclusion is correct.
Yeah. The conclusion is correct. Yes. No. So the intersection, only the product has been. I mean, all the techniques have been defined. So my tomorrow's lecture is supposed to give an overview of chapter 6 and chapter 8 of Fulton. So. Anyway, this was the classical stuff. Okay, anyway, I'll just quickly write down the proof and then then we can stop. Okay, so so write so write this C prime intersection x cross P1 as a linear combination of subvarieties, and then this will be of dimension s plus 1, right, inside x cross P1. And so you know that these coefficients will be positive by this thing about intersection multiplicity that we proved. Okay, so for proper intersections, the intersection multiplicity is positive for the constant. So what do we have? So we have this C dot x equal to this Z plus summation mj zj. This is equal to summation nl el0 as in the. So this computation is same as, so in the previous proof we cooked up a cycle gamma using this, and its section over 0 was exactly this C dot x, which was this, and the section over infinity, the fiber over infinity, it was something that was intersecting correctly. Okay, so this is what this is the same thing that I am writing. Okay, so now so so what can you say about these EL zeros? So these are inside, I mean, as schemes, as subvarieties, these are inside C intersection X, right? So now from this, can I say that these EL0 and alpha intersect properly? See, the infinity part of this cycle is properly intersecting all Wi infinity T's. I mean all of, Wi0 T's and Wi infinity T's. Okay, so this intersects alpha properly, and if you take gamma, which is the part over infinity of this cycle, so this properly intersects so now from this I want to claim that, okay, so from this I want to claim that gamma intersection alpha is rationally equivalent to 0. Okay, and now I want to apply the lemma to this EL. See, the lemma was for subvarieties W of x cross P1, and it said that V dot W0 is rationally equivalent to V dot W infinity. So I will apply the lemma to EL, and then I will get that alpha dot EL0 is rationally equivalent to alpha dot EL infinity, and then that will finish the thing. Okay, so lemma applied to L implies, and plus linearity implies that alpha dot L0 is rationally equivalent to alpha dot El infinity, and so ultimately we wanted to compute this, right? So we had assumed beta to be z, and we wanted to show that this cycle is 0. So now from this equality you write z as the difference of this and this, and then compute. So this is alpha dot this summation NLEL 0 minus summation Mj Zj. Okay, so now by the induction hypothesis, you know that alpha intersection with this part is 0. Okay, so this is rationally equivalent to alpha dot with this infinity with this 0 part of this cycle, and then this is rationally equivalent to alpha dot the infinity part by the lemma. Okay, so the lemma is used again. Okay, so okay, and so this is so what is this? This is nothing but, so my gamma was this, right? So this is rationally equivalent to 0. So that kind of gives an outline of the proof of basic moving. So there was another strong moving which was saying that you can define the intersection class on the subvariety whose push forward will be the intersection class. That is apparently controversial and wrong. So is what everybody says. So yeah, but anyway, as the byproduct of Fulton's theory, all the formulas are correct, and so I think in tomorrow's lecture so of course there's very little time to look at chapter 6 and chapter 8 of Fulton, but I'll give an outline of how the intersection product is defined and what compatibilities and functorialities it satisfies. Okay.